Okay, so we're going to continue talking about empirical formulas today and cover a new subject, which is molecular formulas. So, first, sometimes when you are trying to find an empirical formula, sometimes you don't have mass values, like you don't have grams. Sometimes you have percentages. If you have percentages, it doesn't change too much about what you're doing. All you do is assume a sample size of 100 grams. Okay? And the reason we do that is because if we assume that our sample set is 100 grams, then any percentage that we have, we can use as if it is mass. Right? So, here we have a compound, and they tell us the percentages. It doesn't matter whether my sample size is 1 gram, 10 grams, 100 grams. If you have percentages, you can find the empirical formula. All you do is use these numbers just like they are grams. So 32.37 grams of sodium. So mole of sodium is 23 grams, right? All right, so this is about 1.407 moles of Na. Remember, the first step in empirical formula problems is to find the moles. 22.57 grams of sulfur. A mole of sulfur is 32.07 grams. So this one is 0.7038 moles of sulfur. And then 45.06 grams of oxygen. So we get these numbers. I've got all of my elements into moles, and the second step in empirical formulas is to divide everything by whichever number of moles is the smallest. The smallest value here is 0.7038, so I'm going to divide everything by that. Okay, so the first number gives me 2, roughly 2. It's a number that is clearly intended to be 2. 0.7038 divided by itself, of course, is 1. And 2.816 is going to give us 4. All right, so I have numbers for each of the elements. Now I just assemble them. Lowest electronegativity is sodium, and then sulfur, and then oxygen. And that is my empirical formula. Okay? So no big deal. If they give you percentages instead of grams, it really does not change anything about how you do it. You convert them to moles. All right? All right. So remember when we started talking about empirical formulas, we said empirical formula is the simplest ratio. And a molecular formula is the actual formula. All right, we brought up hydrogen peroxide as an example. Right, H2O2 versus HO. So we need to find real, actual formulas. But in order to do that, you must find the empirical first. So now that you know how to find the empirical formula, we can go to the next step and find the empirical formula. And here's how we do that. So take this example here. So we worked out a problem, okay, and we determined that this is the empirical formula, C2H5. All right? Now, the first step is to find the molecular mass or the molar mass of the empirical formula, C2H5. So there's 2 carbons and there's 5 hydrogens. So the mass of C2H5, the molar mass, is 29.04 AMUs. Or I guess in this case, grams per mole. Both units would be acceptable. That's the first step. Find the molar mass of your empirical formula. Okay? All right. The second step. Divide the molar mass of the molecular formula by the molar mass of the empirical formula. Now, the molar mass of the molecular formula is what is going to be given to you in the problem. The molar mass of the empirical formula, you found this. We just found that, right? So, if we go back to the beginning of this problem, they said the molar mass of the formula is 58.13. We found the molar mass of the empirical formula to be 29.04. So we're going to take a ratio. We're going to divide the molar mass, the actual molar mass, over the empirical formula mass. And here clearly we see we get a number that is 2. So what this tells us that is the molecular formula has twice the numbers of the empirical formula. That's what this means. So to find the real formula, we simply multiply each subscript by 2 to get the molecular formula, the actual formula, which is C4H10. Okay, so you need to have the empirical formula before you can find the molecular formula. So this is sometimes an add-on step in an empirical formula problem. It's really just 2 steps. Right? Find the molar mass of the empirical formula, and then you take a ratio of the molar masses. You get a number. That number could be 2, that number could be 3, 4, 10, whatever. And you multiply. So let's try one. Ribose. Remember ribose as in from deoxyribose? Okay, so it's in DNA, and we know that there's 40% carbon, 6.7% hydrogen, and 53.3% oxygen. And they tell us the molar mass. Now, the molar mass that is given, remember that this is the actual, right? This is the actual molar mass. Determine the empirical formula, then determine the molecular formula. Okay. First things first, we need to find moles. All right, so let's start churning some numbers. Okay, those are my moles of my 3 elements. I mean, you do enough of these and you will be able to look at them and tell right away what the numbers are going to be. What is my ratio? What is my empirical formula just by looking at this? Yeah. Right, because the lowest number is 3.33, right? So if we divide everything here by 3.33, you get a 1C, you get 2 H's, and you get 1 O. So CH2O. This happens to be the formula for seawater. Next time you go swimming in the ocean, right? Just think CH2O. Okay, so that's our empirical formula. They want us to find the molecular formula now. So remember what we said. The first step to find the molecular formula is we got to figure out how much the empirical formula weighs. So let's add these up. So 1 carbon plus 2 H's plus 16. Okay, Okay, so 30.03. This is the empirical molar mass. And the actual molar mass was given to you at the beginning of the problem, 150. So we just take a ratio, right? 150 over 30 is 5. So therefore, the molecular formula will have 5 times the subscript of the empirical formula. So it's going to be C5H10O5. How we doing? That's kind of all there is to it. Molecular formula is a no big whoop. It's just a couple of steps added to an empirical formula problem. Okay? All right. Section 6.3 we already covered. So let's exit out of here.